Okay, B part 4, lecture 21, classical mechanics, spatial translation, Noether theorem. Now this is a continuation of the lecture 20A and 20B. See? So from this lecture we wrote that the action x bar of t plus epsilon of t minus x bar x of x bar is equal to delta s plus order of delta, in this case this epsilon square. So we're going to use this, okay? So let's develop this as the action of x bar t plus this is, it's a tiny displacement, you see, epsilon t. So this is s of x bar t plus delta s plus order of epsilon square. Now you see you follow this equality here. So this is 1/2, this kinetic energy, okay? So the x dot 1 plus this little increment, okay? The tiny increment plus this kinetic energy of mass 1 and mass 2. Now minus the potential energy, you see? x2 plus epsilon minus x1 minus epsilon. So this will cancel here, see? So this leads to, in this case, to this relation over here. So I just copy from here to here, and this is the square, just add x1 plus epsilon dot square. So this is equal to this, plus 1/2, this is the expansion, okay, of this square. So that's easy, okay? Now, I forgot here, no, dt is over here, you see? Minus v, attention now, v is a function of this difference. Doesn't matter is this x2 minus x1 or x bar 1 minus x bar 2. Because v, the potential, depends on the square. So it doesn't matter plus or minus. Then this is dt. You see, this start over here, go there, and come here, there's dt. So I can group, okay? The kinetic energy here. So this is this sum minus v dt plus this, what is left. It's quite easy, no problem. So then I can now attention now, I can compare what we derive here, okay? This is a purple and this is a green. You compare just on this here. So this is quite easy to see it. So this here is the purple, and this one over here, you see, that's the green. You just compare, you see, this term here is the green one, and this term here is the purple one. So that's clear what I'm saying. Now we can compare this with this. So it's clear that this delta S here, the action, is just over here. You see, this is what I can write. Just comparing, and that's quite easy, no problem. So now, from the product or Leibniz rule, just this is a differential of the product. Is u du plus, in this case, is u dv here, is the dv. U dv plus v du plus v du. You see? So this here I can write u dv is the differential of uv minus this is v du. So now you consider this term over here and look at that. So this I call u, this is dv. So it's differential of uv. You see, dv is epsilon dot dt. Okay, then I can easily, this leads to the integral of this is just epsilon. You see, that is v, dv, v. You see, quite easy, no problem here. This is from calculus. Now, likewise, the same, x2 dot epsilon dot dt. Again, this over here and this over here, you just use the product rule. So this is this differential for epsilon x2 dot minus x, attention now, this is dot of dot, this is double dot, see, that's acceleration. So I can substitute easily, so this, you compare, this is delta S over here, you see this, don't forget that this is a green one, you see, this is a green one, see, you just write over there. So easily we can obtain, you see, this is I can integrate, okay, this is I can derive this just using the product rule. This is minus here, you see, this is minus over there, I just copy, no problem. So this is exact differential, okay, the integral of this part over here is equal to 0 if, attention, if and only if this extremum epsilon of T1, epsilon of T2 is equal to 0. This is necessary and sufficient condition to set the action is equal to 0. As I mentioned in the last video, this is stationary, see, stationary path. So then here we can see, you see, this over here, I can write d of dt of this term over here. You see, this one is the same of this one here. So this is d of dt, okay, m1, m2, they are constant, so this exactly is equal to this. This is the total momentum p. So the integral here is equal to 0 because delta S, the green one here, you see, delta S is equal to 0. Attention now, because the epsilon of T1 is equal to epsilon of T2 is equal to 0, you see. So from any epsilon, you see, for any, this implies this, the integrand here is equal to 0. So P here is the total momentum. You see, this over here is the total momentum. I set to 0 because for any epsilon different from 0 implies that the integrand here, that must be 0. You see? So hence, for a spatial translation, the total momentum P is equal constant. You see? Therefore, hence, P is equal constant. So this momentum is conserved. So it's quite easy. You see, to understand this, you just copy, you see, and follow what I'm doing. See? Just the easy algebra, no problem. And also, from calculus, we use the product rule. And also compare with this relation over here, you see? Then you can write, can look at here, look at there, and compare. That's it.